In this video, we'll begin with sample exercise 1. And here we're asked which of these four substances will be most soluble in water. So we should make the consideration which of these substances is most like water. So looking at the first compound here in the upper left, all we see are carbon and hydrogen bonds. So this substance is fairly nonpolar. So we'll just indicate that here, knowing that water is a polar molecule. So here we can see this molecule can OH bond on both ends. So I'll note that's like water. This molecule down here on the lower left that can hydrogen bond with this OH group here on the end, but the rest of the molecule is nonpolar. And then over here, I see all carbon, hydrogen, and then on the right side, I see chlorine. So we have a dipole here. So we have one polar bond. So this is similar to water, being that it is polar, but it's not as similar in the sense that it cannot hydrogen bond. So I'm going to eliminate this choice because it's nonpolar, this choice because it's polar, but it can't hydrogen bond. And then lastly, I'll eliminate this choice because it can only hydrogen bond in one location. So this compound up top here will be the most like water, so it will be the most soluble. So let's take a look at this next section here and see how pressure can affect solubility, mainly the solubility of gases in water. This would increase with increases in pressure. And then in general, we can also see solubility of gases in water would increase with increasing mass. So the heavier the gas molecule, the more soluble it would be. And then we see here the second bullet point that larger molecules will have stronger dispersion forces. We could see that in our an earlier video when we compared the dispersion forces between things like hexane and heptane. So any polar or nonpolar molecule, the larger they are, the more dispersion forces. So let's take a look at this chart here, and it shows us that with increase in partial pressure, so the pressure above the liquid where the gas is dissolved, as we increase that pressure, we can see that there is an upward trend of solubility. So helium would increase, nitrogen, CO, and O2. So that brings us to this equation here and this relationship called Henry's law, where we could define the solubility of the gas, S sub G, as being equal to, sometimes this is KH, you'll see, the Henry's law constant, specific for that gas and that solvent. So this is a very specific constant. Times the P sub G here is the partial pressure of the gas above the liquid. So so that would be what we were increasing here, the gas above our liquid. So let's see how we can use this equation in sample exercise 2. So we're asked here to calculate the concentration of CO2 in a soft drink after the bottle is opened and then equilibrates at room temperature, so about 25 C. So we have the partial pressure is 3.0 times 10 to the negative fourth atmospheres. So we may need that. And then we see down here the Henry's law constant for carbon dioxide in water, which is the solvent in the soft drink, is this term right here, 3.4 to the negative 2 moles per liter atmosphere. So using that equation on the page above here, Sg equals Kh times Pg. So we'll rewrite that over here. So we have Sg equals Kh Pg. And now we'll just plug in these values and then we can calculate our solubility or our concentration. So we're going to see that our units will be in moles per liter. After we cancel out, if we multiply our Henry's law constant here times our partial pressure, we're going to see atmospheres will cancel out in the numerator and denominator. We'll be left with a unit of mole per liter. And we'll see that after we round to two significant figures, our final answer would be 1.0 times 10 to the negative fifth, and I'll abbreviate moles per liter molar. So we'll take a look at some other effects here, such as temperature effects on solubility. And we can see that on the left here, this graph shows a general increase for solubility of a solid. We can see a rare case here with this cesium sulfate, that solubility goes down a little bit with an increase in temperature. So note over here, these would all be solids, specifically salts. And then over here, we're given our unit as just millimolar of gas in our solvent here. And as we increase temperature, so going left to right, we're going to increase temperature, we see a downward trend in solubility. So salts and solids tend to get more soluble with increase in temperature, but gases, we would see a decrease in solubility. So that brings us to our last term here, which I can define something called thermal pollution. So when heat energy, such that, say, a nuclear plant is using water to cool its reactors, when it kind of dumps that water into a local water body, thermal pollution affects the water in the sense that heat will decrease the gas solubility. Important in water for sea life is oxygen. So that is our last topic for this video.